Okay, I always start by saying okay. Right, this is lesson 77, not 777. Come back. Let's be able to... Oh dear, what's happened here? Right, don't want that. There we are. It's lesson 77. Page 208. I've got the book in front of me just in case I need to refer to anything. And it's motion under gravity. If a ball of mass m kilos is dropped and air resistance is ignored, then the only force acting on the ball is the gravitational pull of the earth. The acceleration of the ball is entirely due to the weight of the ball. The weight of the ball depends on where the ball is. If the ball is in space, its weight is much less than it is near the surface of the earth. Note, however, that even if the ball's weight changes based on where it is, its mass never changes. Using Newton's second law, F equals ma, well, the F is its weight only, and the acceleration is the acceleration due to gravity. So we get W equals mg. So an object of mass m kilograms has weight mg newtons. Okay. In questions involving motion on Earth, you will be told which approximation to use for G. You may be told to use G as 9.81 metres per second squared, or even 10. Your answers, you use the same number of significant figures as the value of G you were given. So example 1. Work out the following quantities. The weight of a car... work out the weight of a car of mass 1230 kilograms. Okay, you may assume that G is 9.8. Okay, so straight away we think, right, two significant figures. Okay, and then the weight, which is M times G. So it's 1230 times 9.8, which is 12054 newtons. But we want its two significant figures. So the weight is 12 with 3 noughts. Two significant figures is there. Newtons. The weight of a piece of paper of mass 4.54 grams. You may assume that G is 9.81 metres per second squared. Okay, so 4.54 grams. 1,000 grams is a kilogram, so we've got to start by dividing it by 1,000 to work out how many kilograms we've got. Because, if you remember here, it's kilograms for the mass. Now for newtons, we need kilograms. Okay, so this is going to be we've got to 20454 kilograms. So the weight is 0.00454 times 9.81. So we want three significant figures with this one. And that is 0.0445 to three significant figures. Part C. The mass of a cup of water of weight 3.2 newtons and G is 10. So we need one significant figure for this one. So the weight is the mass times gravity. So therefore 3.2 is the mass times 10. So therefore the mass is 3.2 divided by 10, which is 0.3 kilograms to one significant figure. And which is 300 grams if we go back. Right, example 2. A block is pulled along a horizontal surface by a horizontal string. The tension in the string is 40 newtons, as I'm reading this drawing. Oops, that doesn't want to be there. It wants to be there. It's a bit higher. Nope. Seems to think I want to draw it down there or up there. Oh, straight across. Stay. Don't know what's going on there. Anyway, so the string's being pulled there. Okay, tension in the string is 40 newtons. Frictional force, which does actually want to be low down. Frictional force is 30 newtons. The normal reaction is, if you remember, this does come from the floor. Oh, dearie me. Put that there. So this is the box. It's on the floor. Okay, I'm just making it look like it's actually resting on the floor there. Right, so the normal reaction is 20 newtons. So the weight is, we don't know. Okay, so I've got everything on there. Work out the mass and the acceleration of the block. You may assume that G is 10 meters per second. The weight is mg, so that's going to be 10 times m. Right, so let's resolve horizontally. We've got 40 forwards minus 30 backwards equals mass times acceleration. So therefore ma is 10. And we need the m. We want to work out the mass and the acceleration. So there we are. Resolve vertically. R minus 10m. Now this is equals to 0 because it's pulled along the horizontal surface, so there's no vertical motion. So this is telling us that 10m is 20, so therefore m is 2, and that's kilograms. Okay, that's equation 1, that was equation 2. So if we substitute for m in 1, we get 2 times a is 10, so therefore a is 5 meters per second squared. Okay, example 3. A stone of mass 50 grams, or 50 grams, remember we divide it by 1,000 to turn it into kilograms. So it's going to be 0.05 kilograms. Is dropped from the top of a cliff, which is 20 metres above the sea. So it's dropped like this to the sea. That's 20 metres. This has got mass 0.05 kilograms. And the acceleration is due to gravity at 9.8 metres per second squared. You may assume that, yeah, we've done that one. Find the speed at which the stone hits the sea below. Okay, so A, starting speed is 0. The acceleration is 9.8. The distance that it travels is 20, and that's when it hits the sea below. And we need to find the v, the future, the velocity when it hits there. So we've got v, u, a and s. So we use our Suvat equations. And we've got v squared equals u squared plus 2as. So therefore v squared, u is 0 plus 2 times 9.8 times 20. We can say 2 times 9.8 is 19.6. I'll do this up here. 19.6 times 20. So times it by 2, 12, 18, 19, 2, 3. 1 decimal place, and then times 10. So v squared is 392. And I'll just get my phone for the calculator. I'll try and find a calculator actually. Right, so v squared is 392. So v is the square root of 392. Uh, 19.8. But we've got to have it to two significant figures. So it's going to be 20 metres per second to two significant figures. Okay, that's because it comes up as 19.79. So two significant figures is going to be the tens and the units. And the 0.7 makes it go up to 20. State any assumptions you have made. We've assumed that this stone is a particle, which doesn't spin and has no size. We've also assumed that's about the stone, and the weather conditions, we assume there's no air resistance or any other sort of weather conditions like wind. Okay, there's an exercise to do on these. And then example 4. This one even in here, just in case. A bag of mass 10b kilogram is lowered by a light, inextensible string. I'll just join this up here. So this is 10b kilograms. So it's got 10b, that's its mass. So the weight downwards is mass times acceleration, which is mass times 9.8. It says in the question, look there, 9.8. So I found that one. It's light, inextensible string, accelerates downwards. The acceleration, 3b meters per second squared. Calculate the possible values of b if the tension is 41.5. So we've got a T here, 41.5 newtons. Calculate the possible values of B. Okay. So what we've got here is, I know why it's going to come up as possible, because we've got the 3B there, and there, and there. It's going to come up as a quadratic. Okay, so we can only resolve vertically. So downwards, it's F equals ma is what we've got to use, Newton's second law of motion. So we've got the net force, which is 90. This one is 98b. So 98b minus 41.5 equals, so that's the force. That's the net force because it's 98b downwards. I'll call this one minus and this one positive actually. Before I did it the other way around, but that's because it's moving in this direction. 98b minus 41.5 equals mass, which is 10b, times acceleration, which is 3b. So therefore we've got 30b squared minus 98b. So I've taken that off each side. Add that to each side, plus 41.5 equals 0. I can tell by looking that that's not going to factorise. Well, it might do, but I don't think it will do. B is, so to work out B, it's minus the coefficient of the unsquared B, 98 plus or minus the square root minus 98 squared minus 4 times A times 41.5 squashed in. Sorry about that. I'll start again with that one because it's going to be messy. I'll write it under here. I've got a little bit more room here. So B is minus 98 plus minus the square root B squared minus 4AC all over 2a, 2 times 30. Okay, so this is 98 plus or minus 98 squared minus 4 times 30 times 41.5 4624 all divided by 60. It looks to me like there's a typo in the book here. It might not be the answer, but the way that they've set out the quadratic. So check in a minute. Right, so now we've got 98 plus the square root 4624 divided by 60 equals 2.8, or 98 minus the square root 4624 divided by 60, or 0.5. Okay. Yeah, in the book, if you sit on my copy of the book, it might be right in yours. Their division sign just stops underneath there, but it's definitely got to go right to the edge, so don't let that put you off. But they've got the answers right, they've just got a typo in there. So, yeah. But they've still got these correct answers. Now, the units of these, I've just looked in the book, they're going to be metres per second squared. Okay, and that's because well, it's metres per second squared. If that's a 3 metres per second squared there, this is look, it's metres per second squared. Right,